Thank you very much. Thanks to the organizers for this opportunity. I'm going to talk about that, of course. And if you see, there is this structure from Banach Spaces, because this is one of the few places where you can go back. Ideas, these ideas that I'm going to talk about, they are very simple objects, theoretical objects. So they don't have, or they have very few structure. So one way when you don't have a structure is to go to some other place where there is a little more structure, and in this case, it's going to be a Banach space. So this is what I was explaining a little, right? There is this definition. It's a very, very simple. And because it's very, very simple, it's really complicated to know things. You need to invent some other superstructures on top of the ideas. For example, going and trying to understand the quotient algebra, which I didn't do, but many people is doing that. And of course, there are relationships with set theory, with little topology, and definitely with combinatorics. But what we are going to do is to go to Banach spaces, and this is, and you can do that if the ideal is small, it's an F sigma, and I will explain to you because it's a very simple way. Not only that, if it is also analytic P ideal, you can also do that in another way, a little different way. They have to do the two ways to representation. But more important to me is what is going on with what we call C coloring ideals, which is an object which is purely combinatorial. You have a coloring, so this is that. And then from this coloring, and a little more involved than this one, you can define the ideal of homogeneous, you can define the ideal generated by the homogeneous sets. Yes? Graphs. You can think this as a hypergraph, K, as it is written here, as a K uniform hypergraph. What do? You say that you are connected if you choose 0 or 1 color, or, well, there are many. I am thinking into 2. Yes? You can do it in general. So you can choose one of the colors, and then you declare that you are related if the color is this color. Of course, then you enter in the world of combinatorics, these particular combinatorics, and some interesting things are going to show up. This is going to be the main part. It's going to be at the end. It's a little more demanding, certain computations, but this will be at the end. Okay, and this is very important. This is a joint work with Victor Olmos, which is there, and with Carlos Uzcategui. Okay, so I'm going to do that. I'm going to explain how you define what is this representation, and then I'm going to explain little things about what the representation means. In particular, something about summability, which is kind of interesting, although we don't really understand what is going on there. You will see. Then we will represent in a specific way, in an explicit way, in well-known space of in well-known universal spaces like C of 01 or C of 2 to the n. In this way, the moment you represent inside these spaces, which are, in particular, they are Polish spaces, you can use descriptive theory in trying to understand the ideals, right? We didn't do that, but you could. And then the very last part, which is, again, the most, in my opinion, interesting, is about these coloring ideals. Okay. We have that. There is this idea, which is a very, very abstract object, and there are those which are sigma ideals, simple ones, and the summable ones are the simplest one. You have a total measure on an index set S, and then you define all the subsets of S whose measure is finite. K. Mathur, showed that every sigma ideal is kind of this. and this kind is a very important because it's really the key in this kind of. So you can do basically the same thing, except that now you are not using a measure mu, so there is no additivity or sigma additivity, but only sub-additivity. Right? This is what it says in there. Okay? Always in continuous, because you want finite sets, because of several things. This is an important, really. And then in a very, very simple way, without knowing anything, there is 3 ways from this that you can split all these kind of ideas. The summable ideas, which are the simplest one, nothing to say in there. And then there is these 2 interesting ones, which have to do, of course, with how far this phi here is to be additive or sigma additive or the supremum of blah, blah, blah. We will see what it means, this blah, blah, blah. And then there are these non-pathological ideas, which are kind of like the summable ideas, and kind of is a very general. And there are the pathological ideas, of course. And pathological ideas, suddenly, they will be interesting because there are relations with some combinatorial things, okay? Although they are pathological, or they are called pathological ideas. And the pathology or not pathology depends on the phi, yes? I will explain that. Okay, then there is these P ideas when they have a similar behavior. There is this pseudo union, right? And they are really, really interesting. They have much more structure. You can say much more things somehow. And again, there is a similar thing, right? There is the summable ideas, which are really the nicest one, blah, blah, blah. And then Zalewski and Slavek prove that more or less is the same kind of thing. But again, you change. There is a phi here, yes? And of course, there is something else, right? Because it's really something else. Yeah? And again, I didn't write it down, but yes, it is there. Again, there is the non-pathological, pathological, and the other ones are the very simple ones. Okay, so now what is representation in Banach spaces? Well, there are these 2 representations, the C representation and the B representation. The C representation is going to be the representation of any analytic P ideal, while the B representation, which is the one we are more interested in, is for the F sigma ideals, of course, if they are non-pathological, if and only if. So the non-pathological analytic P ideas are going to be of this way, which I will explain, and the same for the non-pathological F sigma ideas. And there is the definition there, unconditionally convergent. The norm, there is a Banach space there. It should be there. I didn't write it down. But the sequence Xn is a sequence in a given Banach space. Yes, you fix a Banach space, finite dimensional, infinite dimensional, whatever you have in mind. We write, I didn't down, I forgot. And Drevnovsky and Labuda prove that every non-pathological F sigma ideal is of this way. The proof is rather simple. Well, now there is the B, which this is interesting, which is very closely related to that, except that you weaken the definition, and instead of saying unconditionally convergent, you say weakly unconditionally convergent, right? And because of general uniform boundedness principle, it is the same to be weakly unconditionally convergent. That these norms, finite norms, are always finite. The norms of the finite sums are always finite uniformly. I put here how you do that, and how you represent an F sigma ideal inside some Banach space, which is going to be L infinity. This is how they did it. Of course, L infinity is a bad space if you want to do something else, some other things, and description of things, right? So, and then we will correct that by going to C of 0, 1 or C of 2 to the n or things of this way. But it's very simple. So I'm not going to go through the details, but it is there. And it's really simple. You change k by n somehow, and it will work. So you see, this is all about it. And in this way, you also prove that x of this sequence, of this phi there, is represented by xn. And this is what I said, right? The problem is that L infinity is not good for what we want to do. Well, this is what I said. It is written in there that this weakly unconditionally convergent is, well, if you put, yeah, okay. What I wanted to say here is that there is a strong relationship in between being tall ideal. Tall ideal means that every set has a subset in the ideal, dense ideal, but the people call it tall ideal. I don't know why, really. This is dense. Every set has a subset in the ideal. So if you have that in ideal and you represent it as a B of x, then suddenly it will happen that there are many weakly null subsequences in there. Indeed, the sequence itself, because it's the same, will be weakly null. And then you can easily prove what is in there. Norm null, x is norm null exactly when the ideal C of x is tall. This is easy, right? Because you want to be convergent, and this is a series in norm. And then there is this nice result by Dremnowski and Labuda, who says that if you don't have C0 inside, then B is equal to C always. Start with a sequence x, and B of x is equal to C of x. So every F sigma ideal that can be represented in a space without C0 is automatically a P ideal. Particular, right? And indeed, the representation that you are using to represent it in this space for B representation is the same for the C representation. And it's not, again, it's not really complicated once you know what to do. Well, working with that and working a little with all these things, you have this characterization, and it's not, again, from the Banach space point of view, it's not really complicated at all. It's simply to go there and analyze a little and then refer to this in order to have that B of x is tall ideal, is a dense ideal, right? When this is true, right? Either you have every sequence has a subsequence which is either norm null, goes to 0, or it is equivalent to the unit basis of C0. So if there is, well, this is obvious what it says there. So if there is no subsequence satisfying one of the two, obviously will be the other one, right? This is what it says. And if instead of if you demand a little more, not only that subsequences are not of certain way, but the subspace do not have something, then you have that, right? Okay, so then there is this, it is interesting, although we don't understand what it will come now, but it is interesting somehow. So summable ideas, suddenly, by the work of several people, among them Filipov and Triba. Well, they were working on summable ideas, and if which ideas can be extended, can be included in a summable ideal, and things of this way. And they found relations with Riemann summability and things which are really unexpected. But then suddenly, recently, they proved that every non-pathological F sigma ideal is included in a summable ideal. So remember that if you represent the ideal in this way, phi of phi, this is not pathological. Maybe I didn't put the definition, but it will come. This is the supremum. We are in omega. We are in n. Mu n. So this is always included in here, right? It's summable. But typically this is all general. So it's not a triviality what they say, right? There is something to say there. Yes, yes, true. No, I don't know. So I didn't. So my impression when I was doing that in this representation in Banach Spaces was that what you are using in Banach Spaces is very simple somehow. There is nothing except what I'm going to say right now. Were very simple arguments about C0, not C0, and yes. So yeah, so I didn't went through that. Okay. Well, then there are these things. Indeed, if you represent in a finite dimensional, then you get the simplest one. This is not complicated. And then there is this a little more complicated, but if you know what's going on, it's not so complicated. Again, that if you have this generalized parallelogram identity in the Hilbert spaces, then you can use that to understand a little more what's going on with the B of C of B of xn. Yeah? Then simply because of what I wrote there, if you can represent in a Hilbert space with an unconditional sequence, of course, in conditional basic sequence in Hilbert are very simple, right? And then it's summable. And you can extend this a little with the cotype, which is what I was doing there. So the cotype is one of these inequalities I have there with some numbers there. I will not go to the definitions. I will mention that, well, it will come in a while. But then there is this very nice inclusions, maybe useless, but so you represent, you have this B of x in a space which has non-trivial cotype. Then it is in between these two ideas, very simple ones. And again, this is a cheating somehow, because probably this is all. But so good, very nice, but this is P of n, so was n of n, so what? And there is this other thing which, so this thing that I said seems to me interesting because again relate the problem to C0, but in different way. Remember I told you that B is equal C if the space do not have C0. If you demand a little more than that, here, having non-trivial cotype is that you cannot finitely represent C0 in the space. And then reformulating everything that I said, if C0 is not finitely representable or representable, yes, in X, then there is some number there between 2 and infinity. This is the cotype. So that you have that. B is equal to C, and you are in between these two. Yes? Again, it's nice to say, but we have no idea, or I have no idea, if this fellow here all. And it might occur that. Not, okay, so now a few bits about the representation, a little better representation on CO2 to the n, and the same, I will explain CO2 to the n because it's easier, more combinatorial, so you could see there is these 3 bases in there, so you can see the things easier than in CO01, but you can do it also in CO01 by making some nice continuous approximations of what I am saying here. Okay, so this is what I said. You define 3. So remember that there was a slide when I wrote down how to represent in L infinity. Well, there is some small modification somehow, clever modification so that you see a tree, you have to define a tree, right? Without entering, define a tree, which has to do, of course, with the representation of phi like the supremum. And then because it's a tree, which is finitely branching, you can embed it into 2 to the less than n. Once you are in there, you are in business. And then a very simple xn, these are the xn's, yes? These are going to be the ones that represent the ideal. I didn't write it down, but this, yeah, yes. It's here. So it's a really simple and understanding what is going on in there. Okay, yes.
What are the
This one. So you have these clopens in here, the characteristic. This is continuous because you are in 2 to the less than n, 2 to the less than omega, and you put this combination. The S of n, you take this is a node, this is a node, yes? It has a value. You put it in there. This. Okay, so again, this is just to convince you that somehow spaces who do not have too many C0s, they are interesting for all these things. Among them, of course, there are the C of alphas, alpha countable, or C of a barrier, or C of whatever you want to say. I prefer this combinatorial way, to me is more useful. And we are going to say a little thing about that, because then this is a good excuse to go through these coloring ideas afterwards. So we're going to say what happens if you represent in C of k countable compactum. And there is this very nice thing, because I told you at the beginning that one of the main things we wanted to do is to understand a little better consequences of the representation. One of them is that if you go to a nice Banach space, Polish, from the descriptive set point of view, then you can use this in order, for example, to obtain these kind of things. Tall. Tall means dense. Every set has a subset in the ideal. But can you do this in effective way, Borel way? Yes? And the answer is yes. I wrote this in here. If the space is small, well, small, I mean, P of k with k is small. And interestingly, yes. Well, yes. Yes, well, there is this thing and finite and all these things. Yes, of course. Yes. Esteban says, okay, you choose all the singletons and then that's it, right? Good, thank you. But it is an infinite. So you want to find, so I said again, every subset has a further subset in the ideal. I could choose a finite subset and that's it. Yes. Tallness means, thank you, that every infinite set has a further infinite subset which is in the ideal. Yes. This is what I mean there. Everything there is infinite, otherwise it's easy, simple, doesn't say anything. And how do you prove that? Well, and then this is where it comes, the colorings and all these things, because the Ramsey theorem can be effective in certain cases. So if you have a coloring Borel, but not only Borel, but continuous, then answer is yes. But answer, because I am thinking in my, so you can choose in an effective way homogeneous zone. You know that if the coloring is Borel, then for every infinite set, there is a further subset which is homogeneous. Yes? If the coloring is open, there is this map in there that chooses you always an homogeneous set. You give me an infinite set, and there is a way. I have a Borel way to produce a subset which is infinite and which is homogeneous for this coloring. Yes. These colorings, as I will write it down there, they are defined out of extensions, natural extensions of these objects, which are called different ways, fronts, barriers. They are not exactly the same, but even uniform families. They are really, so if you think a little on that and you work on that, you realize that this is a very nice way to represent ordinals, countable ordinals. There is a sum, there is a multiplication, and you can think in quite a nice way. Okay, so I hope I explained this well because, yeah, I started a little strange. And this is what I say. Okay, you have a Borel corollary, and this is all, of course, because every infinite set has a further subset which is infinite subset which is homogeneous. And Galvin Prickly, of course, and then you can extend it for more. You can represent every tall coloring ideal in this very strange way with a characteristic, but this is useless in general, doesn't tell you anything. A little more sophisticated is the fact that every tall F sigma ideal is an open coloring ideal. What is that? There are two colors, if I remember correctly, and one of them is open, not the two. And there is a big distinction in between this big. So, exactly what I said. Then they already knew, but Esteban was telling me that this is a long story, maybe coming back from the 80s, maybe. Solovey was working on these kind of things long time ago. That, yes, that you can choose effectively these homogeneous sets if the coloring is small, is continuous, yes? This is what I said, these things in there, these families which have this property that every infinite set has an unique initial part in the family. It's very important, unique initial part. Yes, this is Sperner. You cannot have two, one strictly initial part of the other, right? And it's unavoidable, obviously, because every infinite set has an initial part. And they determine all these clopens, and they determine all these, all these open, all these continuous colorings in rather simple way. Yeah. This is what I said, that they determine them, yes, in a very rather descriptive way. Okay, so this is the result on that if you can represent an ideal in one of these C of K countable, then they always contain a C coloring ideal. What is a C coloring ideal? Well, I already said, but I'm going to remind, is the ideal generated by the homogeneous sets, yes, the coloring. Well, and of course, there is this barrier there, front, which is a pre-compact. I think I wrote it down. Pre-compact, so you cannot accumulate in any infinite set because remember it's Sperner. So how you are going to do it? You have to go below always. You cannot go above. So if it is countable and compact, then it has a Cantor-Bendixson rank. This Cantor-Bendixson rank has to do with the Cantor-Bendixson rank of the compact, okay, in there, right? There is a little more extra information how we have that. And then there is this for C0. This is the simplest case. You can represent in C0 and tall, if it is tall and represented in C0, if and only if. Well, okay. If you can represent it in C0, then it's tall, if and only if I can find a very simple. Simple in the sense that here is 2, right? But might not be simple. Coloring ideal of this way. exact, yeah. No. No, we did simply we were going there. No. There are many open. If you see the preprint, there is many open things. There are questions that we don't know. Many. Yeah. Okay. So what is okay? So there is this thing. If you were paying attention a little, I was talking about pathological, no pathological, and then there was this C coloring ideas, but I didn't say or didn't mention if they are pathological or not. And it turned out that this is a very interesting thing, maybe the most interesting thing of what I said, which indeed has nothing to do with the Banach spaces, but okay. We arrived to this by this way. Yeah, it does, but I mean, it doesn't. Okay, so yes. So we found out because of that, but really it was one of these coincidences. Okay, so well, indeed, you can improve a little this result here, and this coloring that you find there is indeed a good one. It's a coloring which is good in the sense that the ideal is non-pathological. Yes? Well, hypergraphs. If you don't like colorings, you can think on hypergraphs or graphs if these two. In the most obvious way you can imagine, right? There is the coloring, you take the pre-image of the color, one of the colors, and this is the hyper connections. Hypergraph, and then you might think which kind of hypergraph, the chromatic number, many things you can ask, and this has a reflection in the ideal. The ideal will so some things, some properties of the ideal will be equivalent of properties of certain hypergraphs or certain colorings. Yes. And here, and of course, they are. If the family is N to the D, then these are D uniform. All the connections have the same cardinality. But you could do generals. Okay, so, and there is this big question in that, which we don't know, maybe it's known, but we didn't find, nobody cared on that, maybe, this is the reason. If the random ideal is non-pathological, we have some answer on that, but not for this, but for the other. Well, I put it as a question, but we know the answer. All these hypergraphs, D uniform, I say limits, so more than universal, so ultra homogeneous in the category, and that they exist, so similar to the random graph, Rado graph. We know that the ideal of cliques and anti-cliques, or hyper-cliques or hyper-anti-cliques, this is non-pathological if D is almost 3. Is at least, excuse me, what the hell I said. If it's at least 3, but not for 2. Okay, so this is what I said, that there is this connection between the things. Okay, but there is a little piece of good news on that. And more than because, and the reason why I believe it's good news is because it's using a very nice result in combinatories, the Dilworth theorem. Those nice things that you can explain. I did here. So for certain colorings that are defined, these Sierpinski colorings, yes, when you have an ordering in N and you compare and you say 1 if they agree, 0 if they disagree, for certain colorings, they will come later on, certain, the ideal is non-pathological. And the way we prove it is by Dilworth, right? There is this very nice duality between chains and between anti-chains. Well, there are this other one, between anti-chains and splitting the, yeah. Did I say okay? Or you don't care? No. The Dilworth because we have several statements. One of them is Dilworth, and the other one because there is an asymmetry in the things. The other one is trivial. The other is very simple, and the result in ideals is very simple as well. But so you yes. For the really interesting one is the Dilworth. Yes. But we wanted to see, yes, at some point you see you are doing that and you say, okay, what happens if you change this by that? And then it appears that there is this one which is way easier to prove it. It is a triviality. Yeah, okay. But it has a little consequence. So that's why I see. Uh-huh. So, okay, so if you have that, so and one of the two was because, so you have a partial ordering, so there is a transitivity thing there going on, which is strange, right? If you have m less than n less than d, p less than p, and you have that the coloring of m and n is I, and the coloring of n and p is also I, then the coloring of the first and the third is also I. Right? So this is kind of, well, this is what I'm saying. And if one of the colors is, and if indeed, I think this is the simplest one, this is Miskin application, but this is not. So if the other color is small, as small, then the ideal is non-pathological. So I wrote it in this way because one of them is a simple one and the other is not simple one. Okay, so in particular, of particular interest is these Sierpinski colorings when you have an enumeration of Q. I don't have too much time. Run. So, okay, so what do I do? Well, there is this enumeration, and there is, again, you say 1 if they agree, and 0 if they disagree with the normal, with the canonical ordering of Q. Well, Q, from a combinatorial point of view, is very interesting, 2 to the less than n. Really interesting because they have, it has anti-Ramsey results, but not so bad. I will explain in a while. Okay, so there is first this very interesting thing, which you give me any coloring C with L many, L can be 2 to the 2 to the 2 to the 2 as many times as you want. So I can find an infinite set so that by this enumeration, what I get is a copy or the isomorphic copy of Q, and so that the homogeneous of the coloring here, this natural Sierpinski one, is included to the coloring. So they are universal below. And the statement, the first statement is that there is this very nice result by Galvin, who says that if you color the pairs of Q into L many colors, L is 2 to the 2 to the 2 to the 2, whatever many you want, then I can find a subtree, very nice subtree, looking like Q. So that there I am using at most 2. Only 2. Maybe 1, but at most 2. Yes, but yes, and it will be, yes, but let me go there because I don't have time. I did it. So you can extend this to D, many of them. Then the patterns, there is no 2. The magical number is not 2, but TD, which appears to be the tangent number, the odd tangent number. And I took that from Estevo's book. This is the 16 one, K equal 3. Indeed, D equal 3. Simply copy and paste. He was using K, I'm using D. Because you see Q as binary 3, and you need to understand really well how they behave. You give me D many points there, and you really need to understand the canonical way they are placed one with respect to the others. And this is how they look for 2 and for 3. These are colorings, and they are unavoidable, and these are the ones, right? In general, you can do it for all these. Okay, anyway, and then you can do the same for this, and then you have for colorings of n to the d, you can do a similar thing. I'm going to run super run. So, okay, non-pathology. I was already talking. I didn't say the definition. It is that, right? So it is a supremum of measures below. An ideal is non-pathological if you can represent it as a phi of a non-pathological one. So it's a little more than the phi itself. This one is non-pathological, but there is another one maybe, or there is no if it is pathological. Okay, so I is pathological if you cannot be represented into a Banach space. There is this Masur ideal, which I'm going to go very fast. It is really interesting, but I don't have a time. So you have to define an ideal, which is F sigma ideal. So let us understand what we have to do. Phi of psi, and this psi has to be very bad. Not only this psi, but any other psi who represents this ideal, right? So the goal is to find this psi, and this psi has to be really, really bad. So what are the criteria you can use? So how do you define that? First of all, in general, and secondly, what is the criterion you can use in order to know that this is a bad one? Well, there is this Kelly covering number, which has to do with coverings, and there is a coverings in order to define some measures in general. You have a covering of a finite set. For a subset, you can define the minimal amount of them so that you can cover the set. This is sub measure, and this is some very canonical, very natural way to define it. This is what he does in a very particular way, very particular case. And there is this Kelly's covering number, which is telling you that if you have a measure mu and you have a covering, then there is a tight relation between the two of them. You cannot do just about anything. The sub-measure he's defining violates this inequality there heavily. And that's why the ideal that you define is pathological. You have to prove it, right? Okay, so this is written in there. So, and these are the details. I will leave these slides here so you can take a look. Unfortunately, I did it very badly, so the time is run. It was too slow. Things which are not so interesting, in my opinion. Anyway, so it is in there, how you prove it. And then what we did is to simply go in there, understand what he was doing, and trying to find colorings, because we want to find colorings, right? This is the thing. And the colorings at the end going super fast and not very nicely way. So I want to go not so fast, yes, I go very fast. I knew. I didn't know. Okay, so this is the thing. At the end, there is hypergraph there, and you need to prove that so all this boils down to some combinatorial business. That some graph, very particular, very canonical graph, hypergraph, excuse me, the chromatic number is big or is not. And then you need to prove that. And in order to prove that, which to me is the nicest thing, the way we do it is by using probabilistic business, concentration. I don't know how to do it. We don't know how to do it, but with a probabilistic methods, you can. This is what it is in there, and then there is these nice things. Applications. If you have these sets which has cardinality almost d, n over d, right? And you color them with how many colors. If n is big enough, then you can find a monochromatic set who has cardinality d plus r that covers, and this is the key there. They cover all n. If you do probabilistically, instead of having d plus r, you have d plus 1, but then they will not have this cardinality, exact one, but almost. These are the things that you always have. Okay, so then there is this, the random, the uniform hypergraph is super pathological because it's not included in any non-pathological one, etc. And there is a random graph, of course, that we don't know what to do. And thank you, and let me put that. Thank you.